Welcome everyone, and today we're going to be looking at this tutorial sheet, the tutorial sheet 1 for physics. And this tutorial sheet is actually on the first unit that we learned. I already taught that part, and if you didn't attend, it's better you go back to my YouTube and try to go through the theory or the principles before we start answering, or before you start answering these questions. So we already did stress, strain, elastic moduli, and also we did the properties of fluids, the mechanical properties of fluids. We already talked about that. So this tutorial sheet is basically on those concepts, and without wasting much time, let's go to question 1, which is on density and specific gravity in medicine. But A is saying a sample of bone tissue has a mass of 95 grams and occupies a volume of 60 cubic centimeters. Calculate its density. Determine its specific gravity, and why is specific gravity an important consideration in densitometry? Why is specific gravity an important consideration in bone densitometry? Okay, so this is question 1. And question 1, we've been given data. So label this as question 1, and we've been given data. We've been given mass, 95 grams, and we've also been given volume of 60 cubic centimeters. Like this. So part A is saying we should calculate the density of this guy. So density is equal to mass over volume. And here, since we've already been given mass in grams and volume in cubic centimeters, there's no need of us converting to any units. We can just use these directly and find our density. So density here will be equal to 95 grams over 60 cubic centimeters. And this is going to be equal to what? This is going to be equal to 1.53. Well, let me write it down here. This will be 1.583, sorry. 1.583 grams per cubic centimeter. So this is the density of our sample of bone tissue. So density is equal to 1.583 grams per cubic centimeters. That is part A. Then we have part B. Part B is saying we should calculate the specific gravity. Now, if you remember the definition of specific gravity, we said it just gives us the ratio of the density of the substance we are looking at to the density of water at specifically 4 degrees Celsius. As we said, water is mostly dense at the temperature of 4 degrees Celsius. We already talked about the properties of water, and that's basically what specific gravity is. And we said also to say the density of water at 4 degrees Celsius is basically 1.0 grams per cubic centimeter. So we're going to compare the density that we found here and the density of water at 4 degrees Celsius, and that ratio is the one that is going to give us the specific gravity. So we're going to say SG, which is basically representing specific gravity, will be equal to density of substance over density of water at 4 degrees Celsius. So I can just say at 4 degrees Celsius, like this. And this is going to be equal to what? This is going to be equal to 1.583, which is this density we've calculated here, divided by the density of water at 4 degrees Celsius. So this is 1.000 grams per cubic centimeter. This was also grams per cubic centimeter. Let's say grams per cubic centimeter. And we're going to get our specific gravity, SG, as equivalent to 1.583 grams per cubic centimeter. Or rather, this is a ratio, so the units are going to cancel out. Okay, so these and these are going to cancel out, so which means even our specific gravity is going to be unitless because it's just showing us the gravity. Okay, just like that. So that is the specific gravity of our bone tissue that we've been given in this case. The next question, which is part C of our question, is asking to say, why is specific gravity important in bone densitometry? Why is specific gravity important in bone densitometry? So there are a number of points that we can give out of this, but basically this is all about theory, so it doesn't involve any calculation. That means you can look it up wherever you want, whatever website you can use, or a book you can use, a textbook you can use, you can find such information. So one of the importances of specific gravity in bone densitometry is that it helps us to reflect the bone mineral density. I can call it the bone mineral density, and this bone mineral density is actually very, very critical. Or I can say it's basically a critical factor in assessing the osteoporosis and fracture risk of a certain bone. So specific gravity is going to help us to determine the bone strength and also the risk of fractures and bone fracture risk. So while those are one of the points, let me just write them down here. So I can say it helps us to assess bone strength and this fracture risk. Fracture risk. Another point we can talk about is that we already know to say the specific gravity is dimensionless here. And this also allows the direct comparison of bone density measurements, regardless of the units of measurements that you've used. So that's also one of the importances of specific gravity, of which we can just call that standardization. So it also helps us in standardization. We can also talk about its use in terms of diagnosis when you're trying to run a diagnosis. The When you talk about specifically bone densitometry, you're going to find that higher specific gravity will generally mean that you are having a much healthier and stronger bones, whereby lower specific gravity will also indicate that you're having lower mineral content of your bone. That is going to imply that there is bone weakness there, and also that there is high risk factor to diseases, or maybe there is a disease because there is low mineral content. So I can say it also helps in um, diagnosis. Diagnosis. So I'll just give these 3 points, but you can look it up. As I already said, it's a very, very interesting and simple question, which is only involving theory in this case. So let's look at the next question, which is question 2. Question 2 is saying is about stress, strain, and Young's modulus in human tissues. And question 2 is saying a ligament 5.0 centimeters long and 0.50 centimeters in diameter, stretched by 0.12 centimeters when subjected to 250 newtons of force. A ligament a ligament 5.0 centimeters long and 0.50 centimeters in diameter, stretched by 0.12 centimeters when subjected to a 250 Newton force. But A, calculate the stress. But B, calculate the strain. But C, determine the Young's modulus of the ligament. D, compare this value with that of synthetic ligament materials used in ACL reconstruction. Okay, so this is also a very, very interesting question. Question 2. I'll write it here. Question 2 is about elastic moduli, mostly concentrating on Young's modulus. So we talked about the different types of elastic moduli. We talked about shear modulus, bulk modulus, and also Young's modulus. And Young's modulus mostly it deals with tensile strength and tensile stress. So a force is applied on one end of a substance such that it is going to experience stress in its length. So let's go to the data that we've been given. We've been given the initial length, 5.0 centimeters. We've been given diameter, 0.50 centimeters. We've been given change in length, 0.12 centimeters. We've also been given the force that is applied, and they've given us to say the force applied is 250 newtons. So we can convert these values that we have at the top here into meters, their respective meters, the SI unit. So 5 centimeters, this is the same as 0.05 meters. We've been given 0.5 centimeters. This is 0.005 meters. We have extension, which is the change in length after that application of the force, 0.12 centimeters. And if we convert this one to meters, it's basically going to give us 0.0012 meters. So this is change in length, we have diameter, and we've also been given the initial length and the force also. So the first question was saying we should calculate stress. And we defined, or we related stress to pressure. When we talked about this topic, when we were learning this topic, I related stress to pressure because it's almost the same concept. We're looking at the force that is applied per unit area. So if I bring down the formula for stress, but stress is equal to force applied per unit area like that. And since they've only given us the length of this substance and its diameter, what are we supposed to do? We can calculate its area first before we plug it into this formula. And you know to say for a circular cross section, area is equal to what? Area is equal to pi r squared. Pi r squared. So this is the formula that I'm going to use. So I'm going to say this is equal to force, which is 250 newtons, divided by pi multiplied by r, of which r I'm just dividing the diameter that I'll be given here by 2, which is going to give me 0.0025 multiplied by, oh, this is r squared. So I'll just say r squared. I'll put this in brackets and I'll put a squared there. And I'm going to manipulate this based on the way it is here. So I'm going to say my stress is equal to 250 divided by pi multiplied by r squared. And this is going to give me a value in stress of 1.2, 1.27 times 10 to the power 7 pascals. Okay, so our stress is 1.27 times 10 to the power 7 pascals, of which if I want, I can also write this one as 1.2 or 12.7. Let's convert it into gigapascals or megapascals. This will be the same as 12.7 megapascals. Remember, Pascal, a Pascal is the SI unit for stress. So that is question 1 or part A, which is asking us to find the stress in that particular substance. Let's go to part B. Part B is asking us to find the strain, and we say the strain is just the ratio between the change in length and the initial length. So it depends with what kind of elastic modular you're dealing with. If you're dealing with bulk modulus, you're going to say it's the ratio between the change in volume to the initial volume. And with shear modulus, it's also the same. It's just that with shear modulus, we're dealing with the tiltation. You're applying a force to tilt a substance from its initial form. It's almost like you are deforming it by tilting it to one side, or not really tilting it, but by making it lean to one side. So here we are dealing with Young's modulus, which means our strain will be a ratio between the change in length and the initial length. So this will be equal to delta L divided by L0. That's simply the change or the strain. It's just a ratio and it's dimensionless. So we found our change in length, not we found, but we've already been given to say this is 0.0012 meters over our initial length, which our initial length is 0.05 meters. Like this, that means our strain is equal to 0.024. So this is just a ratio, hence it's dimensionless. Question C is saying we should calculate the Young's modulus, and the Young's modulus is equal to what? Young's modulus is equal to the stress over the strain, and we've already calculated both of those. Stress over strain. So this will be equal to the stress we've calculated to be 1.27 times 10 to the power 7 pascals, and we've calculated the strain as 0.024. Hence, our Young's modulus is going to be equal to 5.29 times 10 to the power 80 pascals. Our Young's modulus will be 5.29 times 10 to the power 80 pascals, of which if I also convert this to megapascals, I'm just going to get 529 megapascals, and this is my Young's moduli. Like that. So that is part C of question 2, and part D. Part D is asking to say what compare with synthetic ligament materials. Part B is saying we should compare this value with that of synthetic ligament material. So this is also, we've already conducted our calculation. The only thing we're supposed to do is compare this value to that of synthetic ligament materials for ACL reconstruction. So this is theory. This is an answer that you can basically find everywhere. You can find it in your books. You can find it in your or on your browsers. You can just try to look it up. But I can just give you 1 or 2 points. So Young's modulus is typically, when you look at most materials, the materials that they are talking about, the Young's modulus of these materials is typically 500 to 1000 megapascals, depending on the type of that particular material and the health. So since we've calculated to say the Young's modulus is 529 megapascals. This is it's slightly on a lower range, but it's within the range, because the range you're expecting is 500 to 1000 megapascals, depending on the strength. So since we calculated 529 rather, we can conclude to say this is a bit on the lower range, but it's making sense because it is falling in the actual range that we are looking for, implying that we are actually looking at a healthy but a bit elastic ligament. Very important point there. And if we also look at the synthetic graft materials, you're going to find that synthetic graft materials such as I can give an example of polyethylene terephthalate, or mostly called PET. This guy, you're going to find that its Young's modulus is 1000 to 1200 megapascals, and these are mostly the much stiffer and natural ligaments. The other ones, the or not natural. Sorry, these are synthetic ligaments. It's stiffer than the natural ligaments, since the one we've calculated is 529. The other ones is polytetra polytetrafluoroethylene fluoroethylene. Okay, so this one mostly has the Young's modulus of 400 to 800 megapascals, and this one is mostly similar and slightly less than compared to the natural ligaments that we've calculated. So that's how you can simply compare the Young's modulus of the natural ligament that we've been given in our question to the Young modulus of synthetic ligaments that they're actually talking about. So this is information that you can actually find in books. Okay, so that's all in question 2. Let's look at the next question, which is question 3. And question 3 is talking about tendon or muscle extension. And the question reads, a muscle fiber 10 centimeters long and 3.5 times 10 to the power minus 6 square meters in cross-sectional area is stretched under a 30 Newton load. If the Young's modulus is 2.0 times 10 to the power 7 pascals, calculate the extension. Calculate the extension. Then the follow-up question is saying, why is elasticity important for tendons and the muscle tissue? Why is elasticity important for tendons and the muscle tissue? Okay, so this is also another interesting question. Question 3. Let's call this one question 3. And question 3, they've given us data, the initial length of the tendon, which is 10 centimeters. They've also given us the cross-sectional area of this tendon, would be 3.5 times 10 to the power minus 6 square meters. Then we have our force, or the load, 30 newtons. And they've also given us the Young's modulus. So it's 2.0 times 10 to the power 7 pascals. Okay, like this. So we can convert our centimeters into meters. This will give us 0.21 centimeters. And I think that's the only thing we're supposed to compare. And we can now bring out the formula for Young's modulus, because what they're asking is the extension. They're asking us to calculate the extension, which means they are expecting us to calculate the change in L. So since we've been given the formula for all, since we've been given Young's modulus, we know to say Young's modulus is equal to stress over strain. of which stress is equal to what? Stress is equal to force over area, whilst this strain is equal to change in L divided by L0, like this. So we can just make change in L the subject to the formula. Let's make change in L the subject to the formula. So we're going to say Young's modulus multiplied by what is down here. Hence, we're going to have F, or let me write it like this. We're going to have Young's modulus change in length over initial length being equal to force over cross-sectional area, like this. And if we rearrange this further, we make change in L the subject formula, we're going to find that we're going to end up with L, change in L will be equal to force multiplied by initial L over cross-sectional area multiplied by the value of Young's modulus. So I can just say Young's modulus. So I represent Young's modulus with y here, but if you want, you can represent it with e. It doesn't matter so long as we end up at the correct answer. So this is the formula that we're going to use in order for us to find the change in L. And from here, we're just going to plug in what we've been given. So our change in L will be equal to the force applied, which is the 30 Newton force, multiplied by the initial L, and the initial L is 0.210 meters. This multiplied by the cross-sectional area, which is 3.5 times 10 to the power minus 6, multiplied by the Young's modulus, which is 2.0 times 10 to the power 7 pascals. So multiply these guys, the numerators and the denominators, and if I plug these in, I'm getting my change in L, which is my change in length, as 0.04286, and this is in meters. If I want, I can convert this into centimeters, and I'm just going to get 4.286 centimeters. So, ladies and gentlemen, that is the extension of our tendon. That is the change in length of our tendon on question 3. And the follow-up question was saying, why is elasticity important to tendons and muscles? So the same applies here. This is a question that you can, or this is mostly involving theory, and it's something that you can look up or just check in your textbook. But I'll give you 1 or 2 points, and one of them is that it's going to mostly be involved in the absorption of shock. So we can say shock absorption, because elasticity is generally going to allow our tendons and muscles to store and release energy during movement. If you're moving your foot, you are constantly raising and dropping your foot, raising and dropping your foot. You're going to find that it is the one which is going to be absorbing the shock to store and release energy during such movements, and by so doing, it will be reducing the impact forces on the joints and I can just say on the bones in general. So it's used for shock absorption. We can also talk about injury prevention, because flexible tissues can stretch under load without tearing. Hence, it will be reducing injuries in terms of strain and such type of injuries which are going to be related with the elasticity of your tendon. So I can just say injury prevention. The next thing we can talk about is maybe the last one. I can talk about efficient movement, because of the recoiling in tendons. Those are the ones that are going to be responsible for improvement in locomotion efficiency by returning the stored energy. So I can just say movement efficiency. Movement efficiency. And ladies and gentlemen, you can look for other points, but that's the end of question 3. That is actually the end of question 3. Let's look at question 4. Question 4 is saying a titanium alloy used, or it's about biomedical engineering application, implants and wires. So the question is saying a titanium alloy used in a spinal implant has a Young's modulus of 1.1 times 10 to the power 11 pascals. A wire of this material 1.0 meters long and 1.0 millimeters in diameter is subjected to 100 Newton force. Question A, calculate the extension. Question B, why must implant material match the modulus of bond? Why must implant materials match the modulus of bond? So this is question 4. Question 4, we've been given data. We've been given Young's modulus that I'll just now represent by E. This is 1.1 times 10 to the power 11 pascals. That's the magnitude of our Young's modulus. Then we have our initial length of the wire to be 1.0 meters long. Then we have diameter of the wire to be 1.0 millimeters. Okay, let me just say millimeters, of which this actually translates. If we convert it into meters, it is going to give us 1.0 times 10 to the power minus 3 meters. Then we also have the given force, which is equal to 100 newtons, like that. So they've asked us to calculate the extension. They've asked us to calculate the extension. So the first thing we can do is calculate the area of the wire. Since they've given us to say it's it's a secular wire, we're going to do the same. Area of a cross-sectional material, of a secular cross-sectional material, will be equal to pi r squared. So since we've been given diameter, we can just say this is equal to pi d. Let me do this. Yeah, basically say pi d over 2 squared. I don't know why I'm failing to rub. Okay, so this is the formula for our area. So we can calculate the area first, and this is going to give us area will be equal to pi multiplied by diameter, which is 1.0 times 10 to the power minus 3 meters, divided by 2, since we want radius, this squared. And this is going to give me my total, or let's break it down first. This will be equal to pi multiplied by 0.5, 0.5 times 10 to the power minus 3 squared, like this. And my area will eventually be equal to 7.854 times 10 to the power minus 7 square meters, like this. So this is my area. And we can now bring down the formula for Young's modulus. We're going to use the Young's modulus formula to find the extension. So the same thing applies. We're going to say this is equal to stress over strain, of which this stress is equal to force over cross-sectional area, or strain is equal to the change in length, which is the extension, divided by the initial length. So I'll rearrange this formula to make change in L the subject of the formula, and I'm going to end up change in L will be equal to force multiplied by the initial length over cross-sectional area multiplied by the Young's modulus, like this, or Young's modulus. So let's plug in what we've been given. We have a force of 100 multiplied by the initial length of 1.0 meters. This divided by the cross-sectional area that we've calculated, which is 7.845 or 854 times 10 to the power minus 7, multiplied by the Young's modulus, which is basically 1.1 times 10 to the power 11. Okay, so I'll plug this into my calculator, and I'm getting my change in length as equal to 1.5, 1.15, 1.158 times 10 to the power minus 3 meters, like this. And this is a very, very small number, and we are capable of converting it into millimeters. Divide it by 1000, and we are going to get 1.16 millimeters. So, ladies and gentlemen, that is our change in length of this material, which is a titanium alloy. This will be the change in length of our titanium alloy. And as usual, they've asked us a theoretical question on part B to say we should do, or why must implants or implant material match the modulus of bond? Why must the implants material match the modulus of bond? So I'll just give maybe 3 or 2 points also here. We can say it is mostly involved in the prevention of stress shielding, stress shielding prevention, because if the implant is too stiff, let's say it has a high modulus, a high young modulus, it is going to be carrying the most of the load, hence reducing the stress on surrounding bone, leading to bone loss. There is a condition that we call osteopenia, which basically means bone loss over time, because almost all the load is carried by the alloy. Since it is very stiff, it is having a higher modulus than the actual bone. So the materials, the implants materials modulus should match that of the bone to prevent stress shielding. So I'll say stress shielding prevention, like that. That is the first one. The second one we can talk about is load sharing. We are expecting, or we expect to say, when we have a similar modulus of the implant and the material, we're going to find that we're going to ensure the bone and the implant actually share the mechanical loads, and that is going to help maintain bone strength and density. So we can say the second point is load sharing. Whilst the third one we can talk about is the ensuring of long-term stability. We're ensuring long-term stability because here also we're going to notice that if the modulus of the implant and bone are actually similar, um, there will be equal sharing, or what can I say? Or if they'll be having matching stiffness. If the modulus of the bone and the implant are similar, they'll be having matching stiffness, which means the stiffness of the bone is the same as that one of the implant. And this one is actually going to ensure that there is reduction in risk of the implant loosening or maybe fracturing. So there will be balance here. The stability of the implant is actually going to be enhanced